Hello, good people. Welcome to video number 2. We are now starting to create graphs of the derivative based on the original function f of x. So we're given a function here. The graph is f. We are asked to sketch the graph of f prime, the derivative of f, on the same axis. Okay, so let's see. What do we notice? I guess we could just make a table like we did last time. We don't even need the original function column. We can go straight to the derivative column, right? So let's pick some points, right? Let's pick at x equals -3, at x equals -1, at 0, at 1, and at 3. Well, actually, we can't. We can't get to 3 yet. Let's see what we find. So when x equals -3, the y value is where this blue point is. So that would be -3. But the slope is the slope of this graph at this blue point, and it looks to be 2, up 2 over 1, up 2 over 1, right? So this is 2. And I think we're going to get a very similar situation as last time where because this is a line and it has a constant slope, that means we can have a constant function for the derivative. So I'm going to fill in the blue values here. But the green values, the slopes at all these blue points, that doesn't change. It's always 2, 2, 2, 2, 2. Also notice the graph somewhat ends here in the picture, but because of the arrow, it continues going in the same manner, right? So it's just a never-ending line. So I'm going to say that my derivative is looking like this. At x equals -3, the slope is 2. At x equals 1, the slope is 2. At x equals 0, the slope is 2. At x equals 1, the slope is 2. So therefore, my derivative function is just a horizontal line. Why? Because the rate of change or the slope of this function never changes. It's always the same. So therefore, my graph is just a constant function because it's a constant slope. So we've done 2 back-to-back examples of linear functions and finding the derivatives of those. But what if we have something more curvy, like these two in example 4? Well, let's think about what we know. We know that if we have horizontal tangents means that the derivative is equal to 0. So these are the zeros on f prime of x. Remember, zeros on the graph represent the x-intercepts. So we're going to, wherever we see a horizontal tangent, usually with a maximum or a minimum, that's a horizontal tangent, we'll be plotting those points as zeros on the derivative graph. We should also remember that if the function is increasing, then we know that f prime is positive. And if we're going to be graphing f prime, that means above the x-axis is the derivative graph. And if f is decreasing, well, we know that f prime is negative, but that means on the f prime, that part of the graph is below the x-axis. If we can kind of have those 3 main ideas in mind when we do our curve sketching, it's going to come in handy. So let's go back over here and we can find, excuse me, what we're looking for. I'm looking at the original function h of x. We are supposed to sketch the graphs of h prime for this graph and k prime for this graph on the appropriate axes. Okay, so let's think about what we said. Can we find any horizontal tangents? Well, there's a horizontal tangent right here at x equals 2. So therefore, my derivative has to have an x-intercept at 2. And then I notice that on this side, my slopes start pretty close to 0, and then the slopes get bigger and bigger and bigger and bigger and bigger and bigger. So my slopes start pretty close to 0, and then they get bigger and bigger and bigger and bigger and bigger and bigger. Now, I'm not talking about the slope of this line. I'm talking about the slopes here. These y values represent that slope. And then on the other side, I notice that these slopes were really negative, and then they got less negative, less negative, less negative, less negative, less negative until they hit 0. So then I would have something that looks like this. My slopes were really negative, less negative, less negative. As I get closer to this point, less negative, less negative, less negative, less negative, until they go to 0. And then my slopes are positive, 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 positive. So positive, 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 positive. So this could be the graph of H prime. It's a line, right? Now, if you think about it, if H is a quadratic parabola graph, and quadratics look like this is standard form, then the derivative of that would be this, and this is a linear equation, which would produce a linear graph. So if you think about the way derivatives work with equations, we can kind of check, especially with some nice curvy polynomial functions, we can check to see if what we're getting looks like what we should get, right? So this was a parabola. That means it's an x to the second power. So if you take the derivative of that, well, then you're going to get a linear function, and that's what this graph looks like. Okay, let's come to the next one. Are there any horizontal tangent lines? Yes, there are horizontal tangent lines. If I can find my handout here. There's a horizontal tangent line here, and there's a horizontal tangent line here. That means that my slope is 0. So this is going to be k prime, and k prime over here as well. Okay, so now think about it. In between these two green points, or in between these two green values, and I'll call it a value, like if, let's say this is -2 and this is +2, right? So at -2, after this 0 slope, I have a positive slope that's slightly bigger than 0, more positive, more positive, more positive, but then less positive, less positive, less positive, less positive, less positive. So somewhere here is the most positive slope, and then it's still a positive slope, but it starts decreasing until it gets to 0. So therefore, I'm going to have more positive, more positive, more positive, more positive, and then less positive, less positive, less positive, less positive. Remember, the y values on this graph are the slopes of the original function. So if my slopes were always positive, that means my graph, or the derivative, which is the slope function, needs to be above the x-axis. And the reason that it turns is because my slopes go from 0 to more positive. My y values start at 0 and they go more positive. And then at some point, they get less positive, less positive, less positive down to 0, less positive, less positive, less positive down to 0. But what happened before that? Well, right before that, I had a negative slope that was pretty close to 0, and then a more negative, more negative, more negative, more negative, more negative, more negative, more negative. So then here, this is going to be more negative, 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 and then we're going to take it all the way down. And the same thing's going to happen over here. I had a more negative slope, more negative, more negative, more negative. Oh no, it's really negative. The slopes are really negative, not the y values, but the slopes are negative. So therefore, I'm going to write these as y values over here that are getting more and more and more and more negative, and I get something like this. What does this green function look like? Or what? Well, this is k prime, by the way. Well, k prime looks like a quadratic, an x to the second power function. But what did the original function look like? Well, the original function looked like a cubic function, an x to the third. And the derivative of x to the third is 3x squared. And that's what this function looks like, right? It looks like a parabola. So we can check with what we know from pre-cal and previous things that we've done with the derivative. We can kind of guess, but we need to practice making the derivative graph and recognizing the derivative graph from the original function and drawing it that way. So that's going to be our task for the next video. Our graphs are going to get a little bit more complicated, but we're going to stick to our guidelines, which are find out where the derivative is equal to 0. Those are going to be the x-intercepts of the derivative graph. Find out where the original function is increasing, because that's where the derivative is going to have positive parts above the x-axis. Find where the original function is decreasing, because that's where the derivative graph is going to be negative, and it's going to be under the x-axis, below the x-axis. We'll come back and we'll practice those ideas.